Cuando tú digas, ¿entiendes? No soy vuestro anfitrión, pero estáis en vuestra casa. Bueno, buenas tardes y bienvenidos ya a la que es la última sesión oficial del Año Internacional de la Cuántica. Recordaros que el lunes que viene a las 12 en el Paraninfo tenemos la sesión de clausura, pero ya la última aquí en la Facultad. Quiero dar la bienvenida a Fabio Sciarrino y a Markus Aspelmeyer, que nos van a dar dos sesiones muy interesantes a priori. Y bueno, Adán Cabello, que es profesor de Física aplicada 2, nos va a presentar a dos conferenciantes, así que Adán.
Buenas tardes, bienvenidos todos. Voy a hablar en inglés. The first speaker today is Fabio Sciarrino. He's full professor at Sapienza, Università di Roma. He's deputy rector for international research policies. He's principal investigator of the Quantum Information Lab at Sapienza, and he works in experimental quantum optics, quantum information, quantum computation, foundations of quantum mechanics, and quantum machine learning. He has received several awards, including the award as Scientist New Talent from the Accademia Pontificia della Scienza Vatican, the Science per la Fisica Medal, the Medal of the Presidency of the Republic, the Sapio Junior Award for Italian Research, and he is currently coordinator of the European FET Operating Project, focusing and principal investigator of ERC Advanced Grants QBells, is also the leader of the Photonic Platform for Quantum Technologies of the Italian National Quantum Science and Technology Institute, coordinator of the European Photonic Quantum Computer. He graduated in physics in 2000 at the University of Naples. He received his PhD in 2004 with a thesis on experimental quantum optics with contributions on quantum teleportation and cloning. He is author of more than 150 papers with more than 22,000 citations, and in recent years he has focused on integrated photonic circuits. So, many things. It is a real pleasure to have you here. Thank you for coming.
Thank you very much, Adam. So good morning, good afternoon to everyone. I will go with that, it's okay. I can do this. So the goal of it's my great pleasure being here. I had a long-standing collaboration with Adam since several years, and my goal is to provide you another view on photonics quantum technologies. I will try to give you an impression on what are the application and how the field is evolving. I will start briefly with a kind of summary introduction, and then I will try to give you some intuition on how the technology is developing, which is at the interface between photonics and quantum technologies. So first of all, let me spend a few words about my labs. It's based in Rome. It's named the Quantum Lab. We have activities on quantum information, on quantum computing and quantum technology, and we are supported by several European and national grants. Also, the goal is to show you how you can use photonics in order to carry out quantum information processing. So let me first give you this overview as starting point that will give you the flavor of the topics we will address. On one side, you have the information theory, where you see the topics of interest within the classical domain. On the other side, you have the quantum mechanics formalism with also different concepts. And the goal today is to discuss how by using photonics one can work at the interface between what is the information theory from a classical perspective and on the other side the quantum mechanics framework. If you want to address quantum properties, you need to work with systems behaving in a quantum way, and one may use a variety of physical platforms. Later on, with my colleagues Markus will see about system with weight, I will discuss how you can exploit this phenomena using particle of light. Oh, I'm sorry. You see in this slide the different platforms which have been developed in the last few years, where one is engineering the manipulation of single particle systems in a way to observe quantum phenomena. You may use particles such as with mass, such as trapped ions called atoms, superconducting systems, spin qubits. I will discuss implementation based on single photons. So the goal will be to generate, manipulate, and detect single photon states, and use single photon states to carry out several tasks. We will discuss about quantum computing especially, but we will also connect with other topics such as communication, metrology, and simulation. Let's say a few words on that. We want to exploit electromagnetic fields. We want to work with a quantized electromagnetic field. We want to consider one particle per time. And we typically work in the visible regime, so where we have most of the technology available today, and we want to encode the information in the property of light. And that will be a key point that we will exploit. So we have electromagnetic field with different properties, where light is propagating, the frequency of light, the timing, and in this different degree of freedom of your field, you want to encode the information. So this gives you a first impression on how it would work. Typically, you fix all the property of the electromagnetic field, and you keep only one free in which you want to write down your information. We will have single particles, and one typical way to encode the information is to exploit polarization of single photons. This means you take one photon, or the wave packet of one single photons, you keep everything fixed except the polarization, and you then write a two-dimensional quantum state in the polarization degree of your single photon states. And this is what we mean polarization encoding. Another way is to encode information in the time. Photons can be emitted at different times. You discretize the time, you divide the time in different slots, and that brings you to the so-called time encoding, where each time slot will correspond to different orthogonal quantum states. And then we have a difference because when we work with polarization, we can only have two orthogonal states. Instead, when you work with time-being encoding, you may have a set of orthogonal states. This means your vector space can have dimension up to n if you have n times slot. And then you may have other properties. Another one is the so-called path encoding. You encode the information in the path where the single photon is propagating. In the picture you see different direction of propagation, different path, and to each path again you associate a different orthogonal quantum states. And then another one, only to give you an overall perspective, exploit what we call orbital angular momentum, which is the transverse profile of your wave packet. For instance, a laser beam has a Gaussian profile, but we have other beam profile which corresponds to different shape of your beam, and you can encode information in the shape. So one can exploit this property one per time, or also you can encode information in the same time different properties. You can exploit time, you can exploit path, and so on. And each encoding is more suitable depending on your technology. I will now show you how you can do quantum information on a chip, and for this kind of manipulation, we will mainly exploit path encoding. So the idea is to have a chip where you will process all the information. So if we want to have an intuition, each time you want to manipulate information, both at the classical level and quantum level, you have three distinct parts of your approach. First, you need to prepare the initial state, in our case, quantum systems. Second step, you would like to manipulate information. And the third step is you want to detect information. And this is what we like to do also when you encode information at the quantum level. You need to prepare a quantum state at the beginning, you want to manipulate it, and then finally you would like to detect it. This before required quite complex apparatus, and now the goal is to have all this device inside the single chip. And in this chip you would like to generate single photon states, you would like to manipulate these single photon states, and then finally you would like to detect the single photon states inside your device. Let me also add, if you have any question, please ask me the question during the presentation. So I would like to give you a bit of intuition on how this technology has evolved and which kind of device one can adopt for the different part. That's a bit what we call photonics integrated technologies, where the goal is to have an integrated device where this different preparation stage, manipulation, and detect can happen. And this gives you an intuition that there are a variety of approaches. You may have the sources which generate quantum states of 1 photons, 2 photons, with different materials and different properties. You will have a manipulation. I will describe this manipulation part as the core of my talk, how you manipulate information of single photons inside an integrated device. And then finally you have the detector. You have detector which have the capability to count 1, 2, or more photons, which again use a variety of technological approach, which go from avalanche photodiode, or which use superconducting detector. As reference, I would like to tell you something about one specific platform we have contributed to develop, which will give an intuition on how you can manipulate quantum state of light inside a chip. And the idea is the following, is to have an integrated circuit inside a piece of glass, which allows you to manipulate in a sophisticated way how light propagates. And this is realized by taking a substrate. The substrate is a glass which is transparent, And then you shine a laser inside the substrate. The laser is tightly focused, is pulsed. Then you move your sample, and by using a multiphoton absorption phenomena, you are able to write down a waveguide inside the material. It's a kind of fiber which is fabricated inside the substrate. This is kind of similar if you go to a room and you can see inside the piece of glass the Colosseum, which is right inside the material. This is somehow similar, but with a much better control. You have a substrate, and we give you now a video. This was taken in Milano, and this gives you an intuition on how the fabrication happens. You may see a substrate which is transparent. You see a lens, a microscope. You see a white spot. The white spot that you see now, that's the laser which has been focused, which is changing the index of refraction inside the material. And then by moving the sample, let me go back to show you again. By moving the sample in different directions, you can realize waveguides with arbitrary geometry, and I will show you several features. You need to have a very powerful laser, pulsed with good parameters, and you need to have a very good stability in the way you are moving your sample. You will move your sample in the three directions, and this will allow you to fabricate the device with the desired geometry. Let me give you an intuition on what you obtain in these cases. You can have this device where these waveguides go in all the directions, up and down, left and right. As I've shown you in the video, the fabrication can be quite fast. So you can have a rapid device prototyping, and you may have a propagation of the light with very good features, which allows you to propagate both classical light, but in our case, we are interested in sending single photon states inside this device. Once you have a waveguide, the first question is, what is the first interesting device to realize? And when you go into the optics, the first device which is interesting is a beam splitter. What is a beam splitter? Is a mirrors with reflectivity 50 and transmittivity 50%. And this is how you realize a beam splitter inside a chip. You have two waveguides where light can propagate. The two waveguides come closer in the central part. And then in the central part, you have a coupling between the evanescent field of the two modes which propagates. And then by engineering the distance between the waveguides and the length, you can engineer how much the two optical modes are coupled. And now if you send light from one side, you will get a coupling between one optical mode and the other optical modes. This is named, in integrated photonics, is named directional coupler, and that's how you get a beam splitter in your integrated chips. That's the first step, that's the first non-trivial elements on which you can manipulate light beams inside the device. Now, what you can have, you can, this picture show you a scheme of the device, and by how changing the interaction length, how the two waveguides are coupled in the central part, how this affects the transmittivity and reflectivity of your integrated beam splitter. You can engineer it, and once it's calibrated, you can obtain the beam splitter with the desired geometry. So this was, let's say, what I will call the entry level, and then the goal is to a bit have an overview on how you can have more sophisticated devices. And I would like to show you a bit how the field evolved and what are the next direction. You can start with one beam splitter, then you may add several beam splitters, all concatenated as shown in this picture, And this allows you to obtain a more sophisticated elaboration on how the systems evolves. You may have different kind of functionality. You may have beam splitter. I'm not going into the details. You can manipulate light of the single photon state on the chip. And all these devices I've shown you are static. This means once they are fabricated, they stay forever with the same functionality. And then what you can do, this is a kind of animation which gives you an intuition that you can increase the complexity of the device, and by adding an appropriate engineering, you can fabricate now a device which have many optical modes, many beam splitter, and you can get something where now you manipulate not more only 2 optical modes, but an increasing number of optical modes. In this case, what you see a device with 5 optical modes, 5 waveguides, light propagate from the left to the right. You see many beam splitter inside your device. This beam splitter allows you in this geometry to couple all the input modes with all the output modes. So now you have realized a matrix which is 5 times 5, which transforms the 5 input modes into the 5 external modes. And again, in this case, as I've told you, once this is fabricated, you get the same transformation forever. The following step can be to not only realize devices which are in one plane, but you can also exploit the capability to fabricate waveguides at different depth. So during the fabrication process, inside your substrate, you can move the substrate up and down, and then fabricate devices which have a 3-dimensional geometry. And you obtain these 3-dimensional devices which generalize what I've shown you before to a more sophisticated geometry. For instance, you have a treater shown on the left side. The treater is a device where you have 3 optical modes coming in and 3 optical modes coming out. And then you may have many other devices. For instance, we use this 3D layout to simulate what happens when you have a maze with a quantum dynamics by realizing a 3D structure which was the replica of a maze geometry. So all what I've told you until now were all fixed devices. And now the question can be, how can we, with an optical platforms, have a kind of programmability? You would like to have a device in which you can turn some control, and by turning your control, you can change the functionality of your systems. And in order to do that, let me again show you this animation. This is again a scheme of the structure where you see you have 6 input modes on the left. You see now how photons are evolving. And the idea is that you are going to locally eat the waveguides. So you have some local eaters made by gold. So gold is close to the waveguides. You apply a voltage. There is an eating of the thermistor. This locally eat the material. The eating will change the index of refraction, and the change of the index of refraction will change the phase. And by changing the phase, you will change the phase of this interferometer, and this will change the transformation. And by having a suitable set of ether, you may have now any functionality realized via this device. So this is what has been done in other platforms. What we have done in collaboration with Milano, CNR, was to have this structure done with a glass substrate fabricated via this femtosecond laser writing. Again, I'm telling you a bit to show you how you have an interconnection between technological development and how you can exploit this technology. So we started with the very first simple scenario on the left side, which is an interferometer, a Mach-Zehnder interferometer with 2 beam splitter. So you have 2 beam splitter, 1 phase in the center, and by changing the phase in the center, you are changing the phase of your interferometer, and you will see the fringe patterns. Then we increased the number of thermal shifters, and this we could carry out different experiments, and I will show you a bit now where we are in terms of platforms. This is a device which was realized now 3 years ago, where you have now a device which have 6 input modes, 6 output modes, and you see the picture of the device, so you may see the connector in red, which are the connector which are driving this thermal heater. You may see the gold part, which are the heater on the top of the chips, and you could see in and out the glass fiber, which are sending the light in and out from the device. And on the right side, you see the scheme of what you have. You have several modes. You see several beam splitters, and then you have the green box, which are the phase that were changing by heating locally the device. So this is a bit more how the structure looks. To give you an idea, on the top you have the concept, below you see how it is physically done. So on the concept side you see this several beam splitters. Each of these beam splitters is done instead by 2 beam splitters and a phase shifter. What is relevant, you have all these phase shifter which allows you to get any kind of transformation you want. This means you can calibrate your device, and by controlling all these 35 parameters, you are able to obtain any transformation going from 6 input mode to 6 output modes. That's the idea. How you do that, you see below, and you see a bit of typical dimension. The chip has a size of few centimeters. The waveguide are propagating close, let's say roughly 80 microns, and you see all the orange below, which are the different thermal heater. Now what you can do, once you fabricate your device, you always have 2 challenges. One is to fabricate something good, and then the following challenge is how you can calibrate a device so that you have the proper control on how it works. And now what you can do nowadays is to exploit also machine learning techniques in a way to get a very good calibration on your device. You take a lot of data, and then by taking a lot of data, you are able to reconstruct how the device is answering to the heating, and this allows you to then get a very good control on its functionality. This is only to give you a qualitative lecture of what one could obtain. Here you see 2 plot which is evolving. On the left side, you see a 6 times 6 matrix which is what you would like to have. So how does it work? You decide the 6 times 6 matrix that you would like to have in the lab. Mathematically, you derive which kind of phase you must apply to your device. You then derive the tension. You have to compensate the different crosstalk. You apply them, and then you compare what you would like to have, the target transformation, to what you measure in the lab. And then you compare the two. And then you may see that you have a parameter which is named F, which stands for fidelity. It's a way to quantify how good is the overlap between 2 matrices. When the fidelity is 1, the 2 matrices are exactly the same, and what you may see that experimentally we have something like 99.5%, which means you have a very good agreement between what you would like to have and what you are able to realize experimentally. And then you see that depending, you find different value experimentally, and always the goal is to increase this value to get very close to 1. So now we improve this value, we have 99.7, and I will show you we have larger chips, and this tells you that you have a technology which is increasing our size, but where your control is getting better and better. Again, if you have any questions, they are welcome at any time. So the goal was to show you a bit a kind of technology which is tightly connected with science, with quantum science. This is indeed from the framework, quantum science and technology. So this is one structure. Now we have to show you another one that we have been also realizing, which is about exploiting the 3-dimensionality. So the idea of having a device which is not anymore on a planar substrate, but where you have a 3D pattern of waveguides which are evolving and which are highly interconnected. And the idea is to have this kind of device here. I will only give you the concept where you have a bundle of waveguides in a chip. In this case, you see 32 waveguides. Now we have 128 in the lab, and we will have 200 waveguides, where light is coupled centrally, and again, you can inject light in and out from your device using fiber arrays which couple your device on one side with a source of photons and on the other side with detectors. And then again, what you can do is that you can exploit this device also with some thermal ether, which allows you to change the functionality of your elaboration. So we are now at the half of my talk, and my goal was a bit to give you an intuition on the physical platform. Now I would like to change and to use this platform to do elaborate information at the quantum level. So we are moving from a hardware description to what we want to run with this device. And to go to the next step, I would like to start from the following question, which was raised now 10 years ago by a physicist John Preskill from the Caltech about the so-called concept of quantum supremacy. The concept of quantum supremacy was introduced by Preskill. You see a tweet from 2012, and the idea of this concept was to name quantum supremacy the regime in which a quantum hardware is able to solve a computational task which is not doable with today's classical computer. And that was the definition, proposed quantum supremacy for controlled quantum systems surpassing classical one. The name that he proposed initially was supremacy. I will call this advantage, and then so the name in my talk will be either supremacy or advantage. I also will comment later on why the terminology has changed between supremacy and advantage. So the idea is the following: we are in the framework of quantum computer, is when we will have a quantum computer able to beat the classical counterpart for some specific task. So the goal is you would like to have a quantum hardware, and then the second, as counterpart, you would like to have any classical computational device that you would like to compare with your quantum systems. That's one of a very good review paper on the theory side of a few years ago, which can be an interesting lecture. Something which I would like to highlight, that this concept of quantum supremacy has been developed, let's say, for experimentalists. In the sense that on the theory side, you know that the quantum computer is better than the classical one. But now the question is, can you go in the lab and build a machine and have a machine that in practice, when you have all the technological challenge, the noise and the imperfections, when you run it, it's doing really better than something else. So you need to combine not only the theory of computer science, but then you have to combine the technology, go in the labs, build the machine, and have the machine doing something better than compared to what you can do today. So I was commenting about the name. There was a debate about quantum supremacy. This was Trump 1 era. And quantum supremacy, let's say, was a bit a term close to white supremacy. So there was a big debate in the main, also in some main journals, such as Wall Street Journal and other, on whether supremacy was the right way to identify scientific goals. And then the debate went into several blogs and so on, and then finally there was, let's say, a common agreement to move from the term quantum supremacy to the term quantum advantage, which is more, let's say, politically well established and does not have any negative interpretation. This is why you see literature, the first paper uses the term quantum supremacy, and then they move it from supremacy to advantage. But the two concepts are the same. So now I would like to discuss in the next 20 minutes how you can achieve quantum supremacy using single photon states. And the idea was proposed by two theoreticians from Caltech, Archip and Aronson, which investigated the following dynamics. They considered to have single photon states of single photons, which evolves into an array of optical modes, which are highly interconnected. So the single photons evolves, they will interfere. You will have n photons and bosons, which propagates over m optical modes. The goal is to measure the output states, which means to sample, to create sample from the output state distribution. And now the question is this task easy to perform classically? Is this task easy to perform with a quantum hardware? And so the first question was, can a classical computer efficiently simulate the output state of these dynamics? It's clear that when you have a small number of photons, that's something easy to do, but what happens when the number of photons is increasing? Is this a task still easy to do, or is the complexity increasing very fast? I will try to give a very simple answer. A very formal answer requires very detailed mathematical explanations, but we may have the following intuitions. When we have n bosons and photons, the wave function must be symmetric. How do you symmetrize the wave function? By doing also permutation. If you have n photons, how many permutations you can do? N factorials. So you expect that you need to symmetrize the wave functions to do n factorial operations, and n factorial grow exponentially with n. So you expect that to do this operation, you need to do an operation which scales exponentially with the number of particles. That's a very qualitative interpretation, explanation. Let's go to a more mathematical one. The more mathematical one is, how do we describe the evolution of n bosons and photons, which evolves on an array of m optical modes? And the mathematical answer is that you need to calculate the permanent of squared matrix. Do you know the concept of permanent? Do you know the determinant of matrix? You know the determinants. The determinant of a matrix, if you have a matrix ABCD, the determinant is AD minus BC. A permanent is AD plus BC. So it's similar to the determinants, but when you have a matrix and you do the permanent, when you do the permutation, you always have to keep the sign plus. While for a determinant, you have always to do the permutation. You have to take into account the sign depending on the permutation. One may say that when you evolve fermions, you need to calculate determinants. When you evolve photons, bosons, you need to calculate permanence. And the permanence is something very complex to calculate. More precisely, the permanence of a squared matrix n times m requires n factorial operation. So, all these arguments, which should be even more formal than what I've told you, tell that this operation is classically hard. In which sense it's classically hard? It grows exponentially with the number of particles. What you can do, you can go on an experimental hardware, and instead of doing this classically, you do this with a quantum approach. This means you will take n bosons and photons, you send these n photons inside an array of interconnected modes, as the one I've shown you before, and you measure the output states. So what you do an experiment which is directly doing this sampling of the output state, and this experiment is named boson sampling. This is how you can do that, and let me show you an animation that will give you an intuition on how this kind of experiments is happening in the lab. So what you need to have several ingredients. The first ingredients, you would like to generate single photon states. So in this case, what you have a laser. The laser is exciting a crystal. In this crystal, you are creating pair of photons. You create pair of photons. In this experiment, we were creating 2 pair of photons, which make 4 photons. The photons that we generate are represented by the yellow balls, which are moving around. You detect your photons, you generate your photons, you then send your photon inside some single mode fiber where light propagates in a very controlled way. You detect one of the 4 photons as trigger, you are left with 3 photons. Now you have the 3 photons inside the fiber, and you will have to have the 3 photons which are synchronized, because you want the light to be so-called indistinguishable. This means you have to do some delay line, which allows you to have the 3 wave packets all synchronized. And this is how you have prepared your initial quantum states. Now you can inject this 3 photon inside the chip I've shown you before. Then light will be injected in the chip, light will evolve and interfere in the chip, and this is where the manipulation will happen. Photons are not splitting. This is a way to show you the superposition principle. This is where you will have your evolution, and then on the output you will have a fiber arrays which allows you to detect all the possible output state, and this is connected with an array of detectors able to count 0 or 1 photons. And now what you do, you run your experiment several times, and each time you run the experiment, you will measure the output state, so the function will collapse on some given contribution, and this is how you measure your output patterns. You will repeat this experiment several times, and this is how you will now sample from the output state distribution. You will get a collection of 1 and 0, and this is the sampling of the output state. In this scenario, we use this for this specific task, but this video could be a way to imagine how is a kind of photonics quantum computer. Single photon states, evolutions, interference, you measure the output, and you collect information. So this was the first experiment that we carried out now 10 years ago. So you see that's a bit a picture of the lab. You see many optics. That's where we were generating the pair of photons. And you see the substrate on the right side, which was the circuit, which at the time was a static one, which means for each different transformation you need a different chip because you could not change the functionality. So only to give you an overview on how the field evolved, I would like to, let's say, last, how much time we have? 5 or 10? To give you an intuition on how the field evolved. In 10 years, you had a strong evolution in the technology, you had better sources of quantum states, you had better chip, better detector, a variety of experiments. I would like to show you this one by China, where the quantum states were generated by quantum dot. So what you can have a quantum dot, which is a kind of artificial atoms inside the cavity, and you can use this quantum emitter to generate 1 photon per pulse, which is also named photon gun, because each shot of the laser you extract from your cavity a single photon state. And this experiment, they used this to carry out the same kind of experiment within a more sophisticated structure. I would like to show you, if you look at the plot gives you an intuition on how large is becoming the hyperspace of your quantum systems. If you look to the end, they could get an hyperspace of dimension 10 to the 14. An Hilbert space of dimension 10 to the 14th means that your wave functions to be described needs 10 to the 14 components. So you have a wave function which is huge. You will never be able to write down your wave function. What you can only do is to carry out some measurement on the quantum state to sample the different components. Then there was a different evolution. Again, different schemes were proposed with different sources in a way to push the complexity of what you could do. And again, I will ask me to show you what happened in the last years, where you see a variety of chips realized also by some companies in Europe, in North America, and also in China, until 2023, where there was this paper again realized, this was realized in China, where they could have, you see a picture of the apparatus, where they could achieve a regime where what you obtain in the lab cannot be replicated by a classical hardware, the so-called regime of quantum advantage. Indeed, the title is Quantum Computational Advantage Using Photons. And in this case, they could achieve a dimensionality of the system with up to 10 to the 30. So you have, in this case, you have something like 100 photons evolving over 200 modes, and the Hilbert space dimension is more or less up to some factors, the binomial coefficient of 200 and 100. And this gives you this huge dimensionality. And then what you can see here is also kind of ingredients that to put together to achieve this regime. Again, a source of quantum states, manipulation, and single photon detections. I would like maybe now to spend the final part, the final 5 minutes of my presentation on showing a bit now what we are doing in my labs, only to give you a bit of intuition of now the next step. We are setting up a platform where we generate single photon states via quantum dot. We send these single photon states in integrated chip, and what we try to do now is to work at the interface between machine learning and quantum technology in a framework which is named quantum machine learning. That's a bit what I've told you before. These are this quantum emitter. There's this quantum dot which behaves as artificial atoms made by several substrates. These are put inside a cavity, and these devices are now provided by a company in France which is named Candela, which is selling these quantum dot sources, where you can have these quantum emitters which are able to generate these single photon states, one per shot. Then, to give you an idea of how these labs now look like, you have a quantum dot sources, you generate this single photon state, you send this single photon state inside the fiber, then you may, from this fiber, inject the light into the integrated chip I've shown you before, where you may have a different functionality that you can carry out inside your device. That's a bit the conceptual picture where one has the sources, the manipulation, and the detections. And that's, again, where our starting point, and the goal is to use this for different elaboration of the information. What you can do, what is a perspective, is you will have to have devices which have more complexity, which means larger chips, more sophisticated sources, in a way to address more challenging tasks with the hardware one has developed. I will then conclude with mentioning two topics in which we have dedicated some effort. One is what we call randomness manipulation at the quantum level. So one may ask how we can generalize to the quantum framework the way we manipulate random variables. Classically, this is named Bernoulli factory. A Bernoulli factory is the way that you have classically to manipulate a distribution of probability. Then you may look to the quantum counterpart and finds that when you do this at the quantum level, you have new properties, which leads to the so-called quantum Bernoulli factory, and this is what we are now investigating with this device. Something else on which I will be very short is so-called quantum machine learning. You would like to encode information in your device and exploit interference between several photons as a way to elaborate information and extract some classification capabilities from your device. And that's a bit a final perspective of where we are now. In order to give you a bit an overview, we have the long-term vision to have quantum computer which will be able to solve problem of interest for the society, and that may be a goal that we achieve, I would say, in 10 years from now. Now they start saying later or before, so the range of prediction is now maybe 5-20 years. Now a question that we're trying to address is, can one find out applications which are of interest, but which do not require a universal quantum computer? And that's something typically which can be at the interface between the computation and the communication. And this is where photons can be useful, because photons are very easy to propagate, to share between different persons, but at the same time they can also be used for computation purpose. That's my final slide. So thank you very much for your attention.
Questions?
Hello. Thank you very much, Fabio. Is it working? Hello. Thank you very much for the talk, very illustrating. I have several questions. I won't ask all of them. So regarding boson sampling, yeah, you were showing some movie with three photons, and you were discussing how to detect the degenerated states by single photon detectors. But I was wondering what about photon bunching? I mean, you can have two photons on the same channel. I mean, there's a tendency by photons to bunch, and you didn't say anything about two photon detections or anything like that.
So, thank you very much for the question. I will answer with 2 points. So for counting the number of photons, now most of the detectors are able to count 1 and 0. Typically, the detector that nowadays do not have the capability to count photons, but what you can do, you can have several bit splitters which divide one mode into many modes, and then by using many detectors, you can also count 2 photons by using coincidence. So you have many detectors, and then you split one mode, optical mode, in several modes, and then you can count even more photons along the same modes. Second point, there is what is named the boson birthday paradox, which tells that if the number of modes is much larger than the number of photons to the square, the events of bunching have an exponentially small probability. So when the chip becomes very large compared to the number of photons, you can neglect in the output the bunching contribution, because they will have a probability which is going to 0. So if you are able to get chip with 100, 1,000 modes, this kind of contribution could be neglected.
Thank you very much, Fabio, for this wonderful talk. It's very nice to see images and how you really produce things. Here we have a lot of engineering students, and I think that they will surely enjoy that. And on the other side, we are used to talk about quantum computing and to listen about how many qubits you have. But you have not mentioned this word just in the beginning. Is this something what you are constructing that can be translated in this more popular number of qubits?
So thank you very much. So that's a very good question, which I've not commented explicitly. So typically one says that one photon is a qubit, but that's a kind of approximation. Because when you have several photons, they are bosons. And so bosons are indistinguishable. Instead, when we talk about qubit, each qubit has a label. Qubit 1, qubit 2, qubit 3. This means that when you do the mapping between photons and qubits, you have to pay attention on how you do the link between the two languages. You can do quantum computing with photons. That's the universal quantum computing, and we have European photons. That is quite challenging because photons are not interacting, so you need to have sophisticated scheme to get the interaction, and that's something on which we are working. And that's how you can map this photonics platform to the qubit language. But let me repeat, one has to pay attention on linking photons to qubit. That's what is interesting here we see in the long-term perspective. For instance, you have, let me mention, we have this EPIC project I'm coordinating at the European level. There are a lot of companies, I mentioned before Candela, which are putting effort towards this scalable photonics quantum computing, and you also have companies in the USA and in Canada, Psyquantum, Xanadu. Something on which now we are more putting effort from our perspective is what we call we started naming photon native algorithm, in which we try to use directly the language of bosonic implementation without relying on the qubit language, because this would save resources. Going via the qubit language requires some extra resources that with the current status of hardware, it's a bit challenging. But also you have an approach to map this photonics platform to a way to scale to the qubit. It's quite challenging because you need many, many components, millions, and this is why you need to go to integrated photonics. Because if you're not able to reach millions of components, that will not work in a regime of interest, which means a regime of quantum advantage.
More questions?
Thanks so much, Fabio, for this great overview. Question of curiosity. So is it then fair to say that boson sampling is right now the only example we have for demonstrated quantum advantage?
So yes, the claim of quantum advantage is always very tough because typically all the claim of quantum advantage has been then, let's say, disproved. Because there was a big advantage on the capability to simulate quantum hardware using techniques such as tensor network. So there was an approach also on qubit based by Google, which was disproved. So it's very difficult to now, you have a very large dimensions achieved both in bosons, but also in superconducting qubit. Knowing which one is really the final quantum advantage is difficult. It's a bit like the loophole-free bell test. No, but in that case, you have the fixed boundary. Now instead, the classical simulation capability has been improved a lot. So I would say it's a gray area of statement, which need to be checked precisely, and there is also a bit of debate between different components. Recently, there was a very nice last paper by Willow, processor by Google, which should be in the regime of quantum advantage. I say should be because so these proofs are, but also on boson sampling, the way one can simulate it improved a lot just in the last few months. So it could be that also the China demonstration are not more standing. So I would say that's some statement to be. We have seen strong improvement. I would not yet be sure about the final condition.
More questions? I have a practical one. We teach quantum mechanics. We say that every unitary operation is physical, and you have a machine that implements every unitary operation. So how much does it cost to have a 6x6 universal chip?
You mean money?
Money, yes.
Okay.
Euros.
So, euros.
Just to talk.
I know, so there are,
For France, price for France. Yes.
so
Yes.
I guess the point is the following. If you want to have this experiment, you need to buy 3 components.
Okay.
You need to have single photon states,
Yeah.
manipulation and detector.
Yeah.
The price, typically this will cost 200,000 kilo euros a source, 300. The circuit will cost maybe 100,000, and the detector today could cost maybe 200,000. But now, so $500,000. It's for free. Let me make the story see. Let's say what I would expect that the cost can go down by a factor 20 in 3 years. Because now you have a capability of doing all this device on a chip, which will make something which was the frontier of science very much accessible in very few years. So that's today, but I would expect that this landscape can change quite quickly.
Hi. When you speak about computing, everybody think in a classical computer. And everybody knows here that in classical computing we use, for example, a compiler to translate for a text to executable software, and you run into a classical computer. But as far as I know, in the case of quantum computing, we only have a quantum gate circuit, but as far as I know, we don't know, or I don't know any compiler for quantum computing machine. How far we are from the compiler for quantum computing machine?
So, that's also topics which is quickly advancing. There was a fundamental paper maybe of a couple of weeks ago that was trying to use quantum computing to compile quantum computing. So something quite new. So something in which you try to devise a quantum algorithm which tells you what is the best way to define a quantum algorithm for some task. So there has been a really quick development of different hardware, software available, which allows you to easily simulate different platforms. Also, the most known one are about qubit, but now you also have one for photons developed by Candela. This means that you have really a variety of emulator available. About this, I have now research going on with first results, but I guess are very, very preliminary.
Sorry, I had second questions then. So regarding the fidelity for the target unitary operations you have for 6 channels, have you done that? I mean, first, have you done that with single photons? Because you also can do it with laser beam, right? In principle.
So I need to be a bit more precise. Thanks for the question. So the 6 times 6 matrix is a matrix with complex coefficient. When you send single photons or classical laser, you can only measure the modulus of the matrix, okay, which is what you see here. So this measurement is done either in the classical or single photon regime. It gives you the same answer.
You had the same fidelity for both?
Yes.
Okay, fine.
But this is only the modulus. If you want to reconstruct the full matrix, you need to measure all the phase. And to measure the phase, you need to see 2 photon interference. So what we do typically, we do a lot of measurement, maybe 5,000, 10,000 classically, so in order to measure, because it's fast. So we may, such a good of photonics, you may use the same device in the classical regime where you can do the measurement quite easily. And then we do maybe 10,000 measurement. Imagine one measurement lasts 3 seconds, it's maybe 10 hours of measurement. And then you can measure also the phase of the matrix, sending 2 photon states, because you need to have quantum interference to see the impact of the phase.
Okay, and you've been using here only path encoding, no?
Yes.
Okay.
So this is a 6-mode device. we have now 12 mode device. A 12 mode device means a device where you have 144 parameters, which controls the transformation. And we have 99.7.
Okay. Just a very brief question. I mean, the channels you define on your crystal may have some, the cross-section may have some eccentricity. And so how good is this for polarization encoding or angular momentum encoding? I mean, is it a problem?
So, you cannot go with orbital angular momentum. For polarization, these devices are polarization insensitive. This means that you can send any polarization state and they are preserved above 99.5, so polarization. So something I've not commented, but we have done an experiment where we also have sent polarization, and it's not manipulating polarization, but it's preserved in the propagation. Thank you.
Thank you very much. Let's thank the speaker again. All yours. Take it. Buenas tardes. Por favor, vamos a seguir. Our second speaker today is Markus Aspelmeyer, who is scientific and executive director at the Institute for Quantum Optics and Quantum Information in Vienna. He is full professor of physics at the Faculty of Physics at the University of Vienna, where he holds the chair of quantum information on the nanoscale. As his own big group, and well, he received his PhD in physics in 2002 at the Ludwig Maximilian Universität in Munich. He joined the group of Anton Zeilinger at the University in Vienna in 2002. And with a postdoctoral fellowship from the Alexander von Humboldt Foundation, and he has received many prizes. The Liebing Prize in 2007, he got an ERC starting independent research grant. the Fresnel Prize of the European Physical Society, the Ignaz Lieben Prize of the Austrian Academy of Sciences, the Fritz Kohlhaas Prize of the Austrian Physical Society. He co-founded a company, Crystalline Mirror Solutions, but you sold it. He sold it to Tor Labs in 2019. He's also wrote many papers and has more than 36,000 citations. It's really an honor to have you here. Thank you for coming.
Thanks so much. Can you hear me? Yes, it should work. Very good. Before we start with the topic of my presentation, let me take the momentum that Fabio generated to remind you on something very fundamental. So we heard about single photons. Okay? So let me just remind you a very simple thing about single photons. So here's a single photon source. We just heard you can buy those now. So then we have the beam splitter. Fabio introduced that, and now you send the single photon to the beam splitter. And what we essentially already heard, and I want to repeat it again, what happens? The single photon does not split. So the photon will either be transmitted and go this path A, or it will be reflected and go part B. So if you now put a detector, which we can also buy, just behind the beam splitter, we will find the photon either here or there, with a 50% probability. This is what quantum physics tells you. And quantum physics tells you you cannot have an explanation whether for the fact that the photon pops up either here or there. This is what we call objective randomness. Quantum physics does not provide you with a causal explanation why the photon ends up in the detector A or detector B. Okay? So now extend that. Let's do what Fabio did, showed you, just in a little, in a less advanced way. Let's just now take the photon that comes here through A. Can you see that? Here on A. And close the loop, send it back to another beam splitter. And the photon that goes through B, we also send back also to another beam splitter. And ask the question now, what is the probability that the photon will end up here? And it turns out, if you make the paths equally long, then the photon will always end up in this detector. Which begs the question, which path did the photon actually take? So now if I'm asking you, tell me which path did the photon take? Well, we know from our previous experiment, if it went, it went path A with 50% probability, so it goes down, it ends up here, so with a 50% probability, it will end up here or there. If it went path B, which also happens with a 50% probability, it will end up again at the beam splitter, and we know what happens. With 50% probability, it will end up here or here. So overall, if the photon took either path A or path B, actually, we expect that, that there's a 50-50% probability. So the fact that the photon always ends up in the output here actually means that we cannot meaningfully talk about that the photon actually had a position and did take either path A or path B. So the experimental outcome here, we do the experiment, Fabio does that experiment, the experimental outcome is exactly that, with 100%, so with certainty it always ends up there. This outcome is inconsistent with the assumption that the photon took either path A or path B. We typically say very loosely, it's a superposition, so the photon took both paths. This is nonsense. It didn't take both paths. We cannot meaningfully talk about position. The only thing we can say is we can perform an experiment, the outcome of which is inconsistent with the assumption that the photon took either path A or path B. So which path did the photon take? We cannot tell. This is undetermined.
This is the fundamental nature of quantum physics. And this is, I just want to emphasize that once more, since we had these beautiful experiments with Fabio, that those photon experiments on using just simple single photons and beam splitters show you the actual core of why quantum physics is actually something that is philosophically really straining. And of course now, if you combine this experiment with a, let's say, more evil device, as Schrödinger did, so you put behind one of the output ports of the beam splitter this thing here, the gun connecting to a cat, then you are forced through quantum physics to describe now this overall situation in a superposition of joint states of photons and cat. Namely, if the photon went through path B, then the cat stays alive. If the photon went through path A, the cat is dead. And now again, we have a state that is a superposition of those two correlated states. We call the superposition of correlations entanglement. But again, it's not that the cat is now both alive and dead. It means that we can create experimentally a state in nature that can create an experimental outcome that is inconsistent with the assumption that the cat is either dead or alive. Okay? This is the whole point. And as you can see, this is from a quote from a letter that Einstein wrote to Schrödinger. He also made it very clear he didn't really like these consequences. That by no art of interpretation can this psi function, so this description of the state that nature can realize, be made an adequate description of the real factual situation. Because in reality, there is no such thing between dead and alive. So much for, I would say, more or less the fundamental problem in quantum physics. Quantum superpositions are awkward, to say the least, and definitely difficult to grasp in our attempt to come up with a worldview that is consistent. How is this connected to the question I want to ask? How does a quantum object gravitate? What do I mean by this question? Let's go back, what's it now, 2025? Let's go back 120 years. So we go back to the very early phase of quantum physics. So Planck has already formulated his quantum theory, and then a young physicist comes along, Einstein, with what is now famously known as the light quantum hypothesis. He writes this beautiful paper on a heuristic viewpoint concerning the creation and transformation of light. So nowadays, the way you typically learn it is, oh, this is the paper where Einstein introduced the photoelectric effect, or explained the photoelectric effect with light quanta. Well, that's not really what happened. Well, actually, what Einstein did in his paper was, he did thermodynamics. This is what everyone back in the days really knew. Everyone was an expert on thermodynamics. Like everyone today is an expert on quantum mechanics. In 1905, everyone was an expert in thermodynamics. And Einstein asked a very simple question. Planck derived his quantum theory using blackbody radiation. So you have a box that contains radiation. The box is warm. The radiation is in thermal equilibrium with the box. And then he asked, well, it's radiation, so I can actually give a value for entropy. So basically for the ability of the gas in the box to perform work. How does this entropy change when I change the volume of the box? That's a very simple, well-defined question. And he computes that. So he says, here's my box with volume V0, I extend it to V1, and then I compute what is the change of entropy of the radiation inside the box. And he comes up with this very beautiful formula that the change in entropy is given by Boltzmann's constant times the logarithm of the ratio of the volumes to the power of something. Then he looks at it and says, that's strange. If I just look at the entropy of an ideal gas, non-interacting identical particles, and increase the volume and ask what is the entropy there, it looks exactly the same. An ideal gas is also entropy change, Boltzmann's constant times logarithm of the ratio of the volume, to the power of n, the number of particles inside my box. Then he says, well, those two are actually the same if n, the number of particles, equals the total energy divided by h bar omega. Which leads him to conclude that monochromatic radiation behaves thermodynamically as if it consisted of mutually independent energy quanta of magnitude, in that case, h times nu. So there was a thermodynamic argument that led him to postulate that light has to consist of particles. And then he said, oh, what would be the consequence? And then he has like 8 appendices to the paper, and appendix number 7 is, oh, by the way, this would also easily explain the photoelectric effect. Ingenious, no? You have to love it. You know what happened? People hated it. Everyone hated it. Max Planck, 1909, this was 4 years after the paper was published. The rejection of Maxwell's electromagnetic waves seems to me to be a step which, in my opinion, is not yet necessary. So basically saying, what the hell did Einstein do? It's just unnecessary. It's nice that you have this theory, okay, but who needs yet another theory if experiments don't require to change the theory? This was 4 years after. Millikan, 11 years after Einstein's paper. Einstein's bold, not to say reckless, light quantum hypothesis flies in the face of the thoroughly established facts of interference. Millikan, by the way, was the one who received the Nobel Prize for actually showing the law of the photoelectric effect that Einstein predicted with his light quantum hypothesis. So Millikan also hated it. Bohr was the worst. Bohr was totally the worst. 15 years later, 20 years later, 1925, Bohr says, even if Einstein sends me a cable that an irrevocable proof of the physical existence of light quanta has now been found, the message cannot reach me because it has to be transmitted by electromagnetic waves. So there was an actual problem there. There was out there this idea that light consisted of quanta, that light is quantized, and no one wanted to hear it. People simply did not like it. And then, of course, later on, quantum electrodynamics came, and then effects were discovered through quantum fluctuation of the electromagnetic field, like the lamp shift, for example. You could measure that in atoms, so it seemed suddenly everything was established. Quantum electrodynamics had to be true. Well, this is not what happened. Well, this is what happened, but actually this was not the end of the story. In the 1970s, famous physicists, for example, like Jaynes, one of the Jaynes-Cummings model, he actually still did not want to believe quantization of the electromagnetic field. He says, famously at the 1972 Rochester conference, physics goes forward on the shoulders of doubters, not believers, and I doubt that quantum electrodynamics is necessary. Jaynes actually came up with a theory based on classical electrodynamics interacting with quantum matter. It was called the neoclassical theory of radiation, but he claimed that with that theory he could keep Maxwell's equations, the basis for electromagnetic radiation, and explain all of the phenomena that quantum electrodynamics would actually predict. This was the challenge for Clauser. John Clauser was also at the conference, and he actually took the challenge, said it is necessary. And the question that was out there in the 70s was, can we design an experiment whose outcome cannot be described anymore by assuming that light is described by Maxwell's classical field theory and matter is described by quantum theory? This was the actual challenge. And Clauser came up with a solution. I don't go into the details here. There was a famous paper by Clauser in 1974 called Experimental Distinction Between the Quantum and Classical Field Theoretic Predictions for the Photoelectric Effect. Essentially, again going back to Fabio's talk, just an assembly of a source of emitting 2 photons in the middle, and then a set of beam splitter left and right, and then measuring photon correlations, or measuring intensity correlations between the detectors. And the main idea was that essentially if light is really a wave, then a wave would split at the beam splitter, and then I would measure a little bit on up and a little bit down. If light is really a particle, then the particle would actually not be split, and I only measure up or down. And if I put that in a mathematical framework, it turns out that correlations between beam splitter outputs would actually violate a Cauchy-Schwarz inequality for intensity correlations. This is the first example, by the way, where a violation of a Cauchy-Schwarz inequality was used in an experiment to demonstrate non-classicality, in that case, of the electromagnetic field. Related to that are, of course, the beautiful Bell tests that were around the same time that more or less have, more or less the same message, but framed differently. So much for the history of quantum optics. What's the situation today? Fast forward to 2025, life is beautiful, we have quantum theory, it works. This is an example of my colleague Markus in Vienna, who does this incredible quantum interference experiments using buckyballs, using large macromolecules. So we have now the quantum superposition principle working not only in the photon level, but also in the level of massive particles that become larger and larger and larger. Perfect. No experiment so far is in contradiction with the predictions of quantum theory. You know what also works? General relativity. It works also perfectly. Here's an example of this fantastic direct detection of gravitational waves only 10 years ago. Many other examples followed were before. There's no experiment so far that we have out there, both on astrophysical scales and in tabletop scales, that would not be in accord with the predictions of GR, general relativity. We have two perfectly working theories. What about the interface? It's even worse at the interface. So at the moment, all experiments that we have at the interface between quantum physics and gravity can be explained by assuming the joint validity of quantum theory for describing matter and classical general relativity for describing spacetime. Rings a bell? Sounds very similar to what we had before. Everything can be beautifully explained by assuming matter is quantized and light obeys just the classical field theory. It's basically it's a one-on-one image of what we had 120 years ago. Two examples. This is a very famous example in neutron interferometry. This is the first experiment that demonstrated that the wave packet of a neutron is actually affected by Earth's gravitational field. It's the so-called cow experiment after the initials of the authors, Colella, Oberhauser, and Werner, that showed that when you have a neutron and you just propagate it through a gravitational field, then what happens, well, quantum mechanics 101, I have a quantum particle, it traverses through a classical external field, it picks up a dynamical phase. We cannot measure global phases, so we need to build an interferometer. So this is what you see here, is a so-called neutron interferometer. That's a single crystal silicon slab with two pieces cut out. So this acts as a beam splitter, this acts as a mirror, this acts as another beam splitter. So we're back to the interferometer level. At the first beam splitter, through Bragg diffraction and transmission, the neutron wave packet is split. The one branch traverses up through a higher gravitational potential, the other one down to a lower gravitational potential. So they each of the branches picks up a different dynamical phase. So if you now re-interfere those two branches, you pick up the phase difference that the neutron picked up while traversing through two different heights of the gravitational field at the same time. You know what that means now. And then what you see here in the experimental outcome is gravitationally induced interference fringes in our neutron interferometer. Beautiful. There are fantastic follow-up works, for example, by Markasevich in Stanford. They recently did the analog of the electrostatic Aharonov-Bohm effect using gravitational effects. Basically, this experiment in a force-free environment, only being sensitive to potential differences. Another beautiful experiment is from Dave Weinland's lab, also some time ago. What you see here is an optical table. You have an optical clock on that optical table. You measure frequency. And then what you do is you just lift the whole experiment, the whole optical table. You see that these are card checks here. You lift the whole table by 30 centimeters in the lab. And what you see is that the frequency changes. This is gravitational time dilation. So clocks tick differently in different heights of Earth's gravitational potential. So what you see here is a direct effect that you're sensitive on changes in the gravitational potential by 30 centimeters in Earth's gravitational field. And recent experiments by the group of Junyi, they actually are now sensitive to height changes below the millimeter scale. It's completely crazy. So we now have quantum systems that are extremely sensitive to gravitational fields, more sensitive than any other classical system has been in the past. Still, in all of those experiments, the quantum systems are extremely sensitive probes of an external classical gravitational field. Which begs the question, in the absence of all experimental necessity of describing gravity through quantum physics, does gravity actually require a quantum description? Okay? So we definitely can write down a quantum theory of gravity. We can do that very confidently. But we can even do it in a way that it's mathematically consistent. At least this is what people nowadays claim, that they do have solved all the problems of the last 100 years of quantum gravity. There are now mathematical problems where we have self-consistent theories of quantum gravity. Okay. Still, it's completely unclear whether nature requires a quantum description of gravity. The mere fact that we can write it down mathematically does not yet mean that nature also has to realize it. So going to another famous conference, we had the Rochester Conference for Quantum Optics. This is the Chapel Hill Conference for Gravity. Austrian physicist Tommy Gold asked, I think, the question in the right way. He asked, okay, can we have phenomena which the classical theory of gravity is unable to explain? The same question that Clauser asked for a electromagnetic field. Feynman was also at this conference, and he jumped up immediately and said, yes, of course. Okay? So what did he have in mind? I put it here in simple pictures. What he had in mind was, well, assume we have a source of gravity, and we are able to put this source of gravity, which creates a space-time metric, in a quantum superposition. And remember, quantum superposition now means that in principle we can perform an experiment, the outcome of which is inconsistent with the assumption that either space-time A or space-time B is actually realized. How would such an experiment look like? Well, we do it exactly in the same way than before. Instead of a photon, we take a test mass particle, a small test mass, and we just let it fall in the space-time metric generated by our mass in a superposition. If the metric also is now in a superposition, then the particle also needs to evolve in a superposition of the metric. Remember, a test particle in a gravitational field falls along a geodesic defined by the metric that the source mass generates. So now we have a superposition of the metric, which means we have to have a superposition of the geodesic, which means the test mass, center of mass, degree of freedom, will become entangled with the source mass, center of mass, degree of freedom, if the gravitational field itself, and hence the metric, is also in a superposition. The problem is, of course, in the same way that Maxwell's field equations don't allow a superposition of charges, also Einstein's field equations don't allow a superposition of the metric. The whole point of a classical field theory is, once I give you any mass distribution, no matter how it looks like, in a box, the metric outside of the box is well defined. There is no space in a classical field theory for a quantum superposition of the metric. So that means, according to GR, our classical theory of gravity, there cannot be any entanglement because the spacetime is well defined, so any test mass will follow a well-defined geodesic and will never become entangled with our source mass. From a quantum theory point of view, of course, we will generate entanglement, which means now you have a yes-no experiment. In that case, if entanglement will be generated, we know GR cannot describe this phenomenon. This is exactly what we wanted. We wanted a phenomenon that cannot be explained anymore by GR. This is it. If there's entanglement, GR is unable to explain it. If there's no entanglement, and we didn't do any mistake in the experiment, we have a problem with quantum theory. Because quantum theory cannot explain the fact that we wouldn't see entanglement. So now we have a decisive experiment. Actually very similar to a Stein-Gerlach experiment. Stern devised his Stern-Gerlach experiment to actually disprove Bohr's quantization postulate. And basically designed an experiment where you have two possible outcomes, and depending on the outcome, it's either classical or quantum, like it is in that case. To make it very quickly a little bit formal, just to put more or less in numbers what I just said. So what we mean is we need quantum sources of gravity. So we need something like a source in a superposition where the states of the superposition are gravitationally distinct. So we can discriminate them or distinguish them with a gravity experiment. This is the whole point. And I say again, this field distribution of a mass in a superposition is not a valid solution of Einstein's field equation. So this cannot be described anymore by classical GR. Now, what do we do with such a thing? We couple it to an observer. So this is now our test particle. We have superposition of the metric through the source mass. We have the superposition of geodesics of the test mass, and through the gravitational coupling we create entanglement. So time evolution will now generate, as you can see here, a superposition of correlations between the source mass state and the test mass state. That's it. Okay? And note, entangling these two systems by gravity cannot be explained anymore by classical GR. So we have fulfilled our task. That's it. So the rest of the talk, I would like to tell you if this is complete bogus or if there's a slim chance that we can realize something like that. Okay? Well, let's do it like that. I show you one number that I put here. Here's the number. So you can ask, just a piece of paper, back on the envelope, how long would it take to generate the entanglement? If I just take two atoms, we can create two atoms, right? We can create two atoms in a superposition, let's say, put them close to each other. So here I say a micrometer separated, and I compute how long it would take through gravitational interaction of the two atoms to become entangled. The answer is, unfortunately, 10 to the 24 seconds, which is, what, 1 million times longer than the lifetime of the universe. That's bad. So now you have two options. So either you close your notebook and you go home and you work on a different project, quantum computing, quantum biology, something like that, or you do a second calculation. You say, well, okay, what if I don't take an atom, but I take two small spheres? Okay, like a lead sphere or a gold sphere. Yeah, like, let's say 50 micron in size. That's still small, like 10 to the 18 atoms in there. I take two of them. I also assume that I can create a little bit of a superposition. I place them next to each other, and I compute how long will it take for entanglement to be generated. I do it. What do I get out? 10 milliseconds. Well, so for an experimenter, 10 milliseconds is actually a reasonable timescale. So that's interesting. So now the question is rather, okay, do we think that we can create quantum systems as large as 50 micrometer and isolate gravitational coupling on distances of some 50 micrometer of such small objects? Okay? So the question has changed now. So what are the challenges? And if you do a little bit of math, so you do one more round in your coffee house, your favorite coffee house, Vienna is good for that, by the way. You do one more round, and then you come up with a condition that your quantum system has to fulfill. And the condition is, funnily enough, that the product of mass, delocalizations, and I'm talking about the size of the wave packet or the size of the superposition of your mass, times the coherence time, times 1 over d cubed, and d is now the distance of our gravity experiment. The product of that, so you see here the two masses separated by d. The product of these numbers here needs to be larger than h bar, Planck's constant, over Newton's constant. I don't go into the details. I just tell you briefly so you can find the details in this paper. The idea is that you simply compute for a couple of different situations, for example, two coupled harmonic oscillators, quantum oscillators, coupled via gravity, what is the entanglement rates that you generate, and this you compare with the decoherence rate. It needs to be larger than that, and this provides you then with this inequality. So if you want to know more details, just ask me. But the main point is, this is the condition that we need to fulfill, and now we can say, okay, let's assume we have two masses, spherical masses, okay, at a distance between the surface of, let's say, 10 micrometer. This is reasonable because if you get closer, everything goes haywire, you have Casimir effects, and you still need to measure gravity. So you need to isolate somehow gravity, you need a Faraday shield in between. So 10 micrometer is experimentally a safe assumption. You want a density of solids like 10 to the 4 kilogram per cubic meter, and you want coherence times that are sufficiently long, let's say 10 milliseconds. It doesn't make sense to assume 100 seconds coherence time because large object means there's a lot of decoherence through black body and so on. So you want small ones. And then basically here's a possible set that could be working. Mass on the, so basically an object of 4 micrometer in radius. So 10, let's say 10 micrometer in diameter. A delocalization of 400 nanometer, so much smaller than the object itself, but still you need a coherent delocalization of the wave packet by 400 nanometer. And that's it. The whole thing at 8 Kelvin and at 10 to the minus 16 millibar, and then you're in business. Then you could generate that. So this would be a target number that you could go for. So now, again, so far, I would say so far it's, we are on track. Okay, so we have numbers now where we want to go, and now basically we need to decide, or we need to ask where do we stand in order to decide what to do. The nice thing about this expression is we can break it down into the left part. You see mass, delocalization, coherence time. These are benchmark numbers for quantum experiments. I can now just do single particle quantum experiments and try to make this number large. Maximal mass, maximal delocalization, maximal coherence time. Okay, so let's push that. And then I do gravity experiments and just see how small I can get in distance and mass and still isolate gravity as the actual interaction in my coupling. Okay? So let's start with quantum. What is the current state of the art when we talk about masses delocalized in the center of mass degree of freedom, because that's what we need. Here's an overview. We have, I mentioned it already, single atoms, so 10 to the naught atoms. We have macromolecules, a few thousand atoms, and then we have this whole domain of quantum optomechanics, which is essentially quantum optically controlled solids. I don't go into the details here. This is actually something, this is how this whole thing emerged. This is actually something we've been working on the last 20 years. And through being able to manipulate solids, or the center of mass of solids in the quantum regime, only the idea emerged that we could use that for gravity experiments. So I spare the history of that. Suffice to say, we are now able to have things like micromechanical devices, nanoparticles, even acoustic modes of bulk solids to be operated, to be controlled in a quantum regime. Schrödinger cat states, squeeze states, non-Gaussian states, entangled states, all of that has been shown already in the lab using quantum optical control method. So this is basically now an established field. The problem that we have is, if you look at the lower axis, so the mass is super. The mass goes up to 10 to the 17 atoms. Great. That, basically my target would be like 10 to the 13, 10 to the 14 atoms. So we are way beyond that. Mass we already can tick. The problem is the delocalization. As you can see, the larger the mass, the smaller the delocalization. So we do have Planck mass objects, so bulk solids with the collective motion of 10 to the 17 atoms in a Schrödinger cat state. The problem is that the according displacement of the atoms is only on the level of attometer. 10 to the minus 18. we have levitated nanoparticles. I will say more about that with delocalizations on the picometer scale. If we, number-wise again, remember, we are after mass times delocalization times coherence time. Okay? That's the number. I call that the gravitational cattiness. And if you normalize that accordingly, such that a value of 1 would be our target number, then you see where we are at the moment. None of the current experiments is anywhere close to 1. You see? 18 orders of magnitude, 20 orders of magnitude, 12 orders of magnitude. And here comes even the bigger problem. The bigger problem is, in most of those experiments, I wouldn't even know which handle to tune in order to jump like another 18 orders of magnitude. Because you would have to change either mass, delocalization, or coherence time. So for a single atom, it's only 12 orders of magnitude. But what can I change for a single atom? Delocalization is already half a meter. If I want to gain 6 orders of magnitude, then I have to have 1,000 kilometers in delocalization in order to come close. And so on and so on. So no matter what I do, which system I take, sort of I do not really know how to bridge this gap, with one exception. This one exception is levitated particles. And I will tell you why. The beauty of levitated particles, so we're talking about trapped nanoparticles, so solid state particles, that right now are in the regime of 10 to the 9 atoms, with a delocalization of picometer. But you know, trapping is something that I can do with masses that are larger than just 10 to the 9 atoms in principle. Those techniques I can advance. And delocalization is something that for trapped particles, look at AMO physics, you can wonderfully enhance. If I have a particle that is trapped in a harmonic trap, let's say, I can use the harmonic trap to prepare a pure state wave packet. So I have to describe now my center of mass degree of freedom with a wave packet. And you know what I can do now? I can just switch off the trap. What happens then? The wave packet just disperses. It grows, it grows, it grows. So already after, in that case, for the example, like 10 milliseconds, I already have a wave packet size that is larger than the physical size of my particle. So in principle, using trapped particles and using control techniques that I know from atomic physics, this has been done with single atoms, I can start to manipulate the wave packet of massive particles to an extent that pushes me where I want to go. I give you just one quick example. Here we have in our group, we trap nanoparticles. This is a so-called optical tweezing. This is very simple. You just focus a laser beam, and because the dominant direction that is interesting for a dielectric particle is just a dipole moment times E, right? So the potential landscape that the particle sees is d dot E, but the dipole moment itself is induced. It's an induced dipole through the external electric field. So the dipole moment is the polarizability times the electric field. So what you get is simply something that is proportional to the intensity. So the potential landscape that the particle sees is just minus the intensity profile. So if I now have a focused laser beam, which is a Gaussian beam, minus a Gauss is for small displacements just an harmonic trap. And this is true for all 3 directions, because a focused Gauss beam is in all 3 directions harmonic to first order. So it means a focused laser beam makes a 3D harmonic trap for a particle. This is why, if I just have here a microscope objective, in the focus of my microscope objective, I can trap particles. I can do this in vacuum, and then I can do many things. For example, I can put a cavity around. So this is now again tricks from AMO physics. I just put 2 mirrors around, and what happens is light is scattered off the particle. I get also inelastic scattering, which means that there is light that actually takes away energy of the particle, and there's light that actually puts energy to the particle. So these are the so-called Raman scattering processes, Stokes and anti-Stokes, processes that take away energy, processes that put energy. And what I do now with this cavity, I just make the cavity resonant to one of those 2 processes, namely to the process that takes out energy of the system. So I make this cavity resonant to the anti-Stokes Raman scattering process, which means just by putting an empty cavity, so just 2 mirrors around my particle while I keep it in a tweezer, automatically laser cools the particle motion along the cavity axis, down, 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 until you reach the quantum ground state of motion. So this is how we actually realized a quantum ground state of motion of this 150 nanometer particle, silica particle, trapped at room temperature and being kept in its quantum ground state of motion. So here's a picture. This is an actual picture of a 150 nanometer glass sphere that is kept at room temperature and is in its quantum ground state of motion. So you see actually here a picture of a quantum object, a solid with 10 to the 9 atoms. You have to describe the center of mass of this thing using a wave packet. And now what you can do is exactly what I just told you. Now you basically just switch off the trap and let the whole thing fall. What we do is we don't let it fall. Our particle is charged, and we actually have electrodes around the, the particle is charged. We have electrodes around the particle, so when we switch off the trap, the particle actually stays where it is. It's like a Millikan oil drop experiment. The particle just stays there. The wave packet expands, and then after some time we switch on the trap again and we measure the size of the particle. And this is something that we have recently done, and you can see we can already expand the wave packet size by a factor of 100. Yeah, just like that. And you see the cattiness is we already improved by 10 orders of magnitude, yeah, in the cattiness. And the next thing is, how do we get the other 10 orders of magnitude? Increase the mass. So what we have right now in our lab, we have superconducting particles. So this is now not any longer 150 nanometer, but you see this is like 100 micrometer. So suddenly those objects are much more heavy, and we can also trap them. The way we do that, these are superconducting particles, we can trap them magnetically. Superconductors are perfect diamagnets, so we have magnetic coils, superconducting coils. We have anti-Helmholtz coil configuration, which make an harmonic trap for dielectric particles. And what you see here is actually in the red circle is a trapped superconducting particle at ultra cold temperatures already. And the next steps are now, in our case, we want to find out whether we can use the same tricks we do with laser light, in this case for superconducting particles. Final comment. So this is a way we think that for quantum systems we are on a way that we can actually get in the right parameter regime. What about gravity? Can we actually measure gravity of small objects? So when we started to ask this question, the smallest object people have measured the gravitational field of was in the order of a gram. And so we said, well, okay, let's do a factor 10 better, just to understand what it takes to do it. So the idea is simple. We thought we take a gold sphere, like a millimeter gold sphere. We take two of them close to each other, and if you change the position, if you modulate one of them, the other one sees periodic modulation of the gravitational field and should also start to move. And of course, in order to do that, you have to isolate it from all other phenomena. So what we built was a so-called Cavendish type experiment. Is a torsional balance. What you can see here is there's a little glass rod with two of these little millimeter spheres. There's a second sphere, and you're moving this sphere a few millimeters back and forth. The minimum surface distance is 400 micrometer, and you generate an acceleration modulation on the order of 10 to the minus 10 meter per second square. So 10 to the minus 11 g. That also means this corresponds to a displacement here of the torsion on the order of a few nanometer. Question is, if you just hang your torsional pendulum in your lab, will it be spilled down to the nanometer level? Yeah, so meaning, can you resolve actually those vibrations? The answer is no. So this is what you see here is a plot that shows how strong the vibration is at certain frequencies. Blue is nothing, yellow is a lot. And this is a function of time. As you can see, this is around our pendulum resonance frequency, 100 millihertz, 10 millihertz. You see there's a strong yellow line. And it turns out this was actually resonant to the traffic light cycle of a road crossing close to our lab. So trams stopping, accelerating, pedestrians stopping, accelerating, buses, cars, and so on and so on. That would all excite our pendulum at 10 millihertz and higher harmonics. Then you see suddenly it's blue. So suddenly nothing. This is between midnight and 5 a.m. when the whole traffic stops running. Yeah, so basically these blue spots here, those give you the window for measurements. There you can measure between midnight and 5 a.m. And then you see there's always 1, 2, 3, 4, 5 dark blue lines, and then 2 not so blue lines. Okay, this is Friday night and Saturday night, where people are out on the street. So basically this leaves you now 5 days, 5 nights between midnight and 5 a.m. for measurement runs. Eventually we use Christmas. So this is then the result after the Christmas break, and here you see beautifully the gravitational peak that resulted from our 1 millimeter gold sphere. So this is the smallest source mass so far that has been measured in any lab. So the gravitational field of the smallest source mass so far. You can also see a second peak here. This is funny, this is a higher order response of the pendulum, because what you're modulating is actually a 1 over R potential. And so Taylor expansion leads to higher order contributions, and you can also see that. So what's next? Let me finish. What's next is now we want to go to even smaller masses. So this one here, can you see this one here? This is our next source mass. Okay, so we want now to have, we want to go down to 100 micrometer instead of a millimeter. And this, as you can imagine, you cannot do anymore in the city lab. No chance. So we have moved our experiment underground. This is actually a tunnel that is in the vicinity of Vienna. The experiment is being built up at the moment, and the performance is really very nice. So we measured gravitation, so we measured seismic noise. You see red is the mine, which is really much better than the city lab. Also magnetic noise is much smaller, and we are now building up the experiment with now these microfabricated masses on the order of the 10 to the 18 atoms. Okay, very good. So that's it. Let me summarize. We know what to do. Okay, so basically from a first back-on-the-envelope calculation, we go to the next levels of back-on-the-envelope calculations. We know that on the quantum side and on the gravity side, we have things like mass, delocalization, coherence time. We have mass, distance, acceleration noise that needs to go down. Green is what we have realized already, and we need all of those columns to go green in order to realize the experiment that we want. Namely, to have an experiment, the outcome of which is likely to be inconsistent with the predictions of GR. So with that, let me thank my team. It requires quite a large team to push that forward, both on the gravity and on the quantum side. And thank you for your patience and attendance.
Okay, so thank you so much for a very really inspiring and interesting talk. You know, when you were sort of giving the talk, something that was somehow, in the back of my mind is that, okay, right, building sort of superpositions of quantum states when you have elementary particles or protons or nuclei or molecules, whatever, that's fine because they do not have sort of they can be described accurately by a pure state and not a mixture. But then when you go, to a ball of some millimeters, why? In order to build a superposition, you need the ball to be in a quantum mechanical pure state, or you can live, with a mixture of internal states.
Yes, no, you're fully correct. You need the mass to be really in a pure quantum mechanical state. And so this is essentially the idea that we are following here. We start with this harmonically trapped particle that we prepare in its quantum ground state, because being in the quantum ground state means that I now have a pure state wave packet. So I have to describe now my center of mass with a wave packet that is pure.
I mean, sure, I understand. I mean, from all the degrees of freedom that your ball has, the center of mass coordinate, I agree with you, that it will be described by the Gaussian or whatever.
Yes, but
then the point is that you have other degrees of freedom. I mean, your ball is sort of vibrating, so in no way you can describe the ball as a...
Thank you very much. I misunderstood the question. Yes, you're right. So now this is a solid object. This is actually all these experiments, while we do that, the particle is rotating at like 50 megahertz. So just as an example, there is this degree of freedom. Then it's charged also, and so on and so on. So the point is that as long as those other degrees of freedom do not reveal anything about the position of the particle, it's fine, because those degrees of freedom then factor out. So that means if there's no, let's say, electric field gradient, such that the particle would behave differently here or here, it's fine. If there's nothing in the environment that would actually distinguish whether my particle is rotating up here or down here, it's fine. So this is what we need to take care, that all other degrees of freedoms do not in any way reveal information about the position within our coherent delocalization. This is what we need to do. And mostly it means uniformity of all possible environmental couplings. Thanks. This is a very important point.
Thank you. Just in connection with your reply to his question. So that's for one single mass. But if you have two masses, which is what you were considering before, I mean, you had some estimations, you never consider the fact that any mass is made out of charges, actually. So I wonder whether the possibility of exciting other degrees of freedom, like charges, is encrypted in the coherence time or anything like that. Because you never mention any specific parameter for that.
Thank you. Yeah, this of course for reasons of time. So I wanted to paint the big picture, but of course, so almost each sentence I said in the big picture has a long addendum of exactly those questions. So concerning the charge coupling, you're fully correct. There's no way that there would not be any. So there's no way that we would not have any remnant charges. So even if the charges would be not present on the particle itself, internal defects would actually already create dipoles that would couple to each other. What is normally done, and what we are also doing in all our gravity experiments, is to use a Faraday shield between the two masses. Okay? So a Faraday shield means that at least the electromagnetic coupling between the masses is excluded. So because what the Faraday shield does is you create, so any sort of electromagnetic configuration that size is compensated through image charges in the Faraday shield. That means I don't have any position-dependent coupling to my other particle. I still have, however, DC couplings now because of that, because of the shield coupling to my particle. So this is number one, the DC forces I will have. DC forces normally do not destroy coherence. However, the fact that I now create image charges means that I localize my particle through the charges. So if there's dissipation in the Faraday shield, I get localization of the particle through the dissipation in the shield, so the Faraday shield introduces decoherence. So this is another boundary condition now, that my delocalization has to be small compared to the distance to the shield. So I cannot, like you read in some of the proposals, I cannot take a mass and make a huge superposition very close to the Faraday shield. It will decohere immediately. Now you need to have a very tiny superposition, which puts now a lower bound on the mass. Because tiny superposition means I need to increase the mass now to have the coupling still strong enough to generate gravitational coupling, and so on and so on. So this gives you a lower bound for the mass on the order of 10 to the minus 6 times the Planck mass. Yeah. Thanks.
Thank you very much, Markus, for this very nice talk. I could ask many questions, but I will focus on the one that intrigues me more. Is how could you be more explicit in describing the effect that you expect for the entangled gravitational field? Would you send? You said you will send a particle to the system, but now you show here a Cavendish pendulum. Could you be more explicit? Thank you.
Yeah, thanks. So the, let's say, very vague sketch, the way you can envision it is that you have, go down here to this configuration, you have two masses, both harmonically trapped initially, or just some wave packets. You have two masses next to each other, and just by sitting next to each other in a 1/r potential, they will become entangled. So essentially now for the quantum optics people in the audience, the 1/r potential effectively generates an XX coupling between the two, which is a two-mode squeezing operation. So this creates an EPR state, an Einzelmodulus-Rosen state in position and momentum between the two, and now you have to read it out. So basically it's really just as simple as two particles with a Faraday shield in between, delocalized as much as possible, a lot of praying involved, and then you need to be able to measure position and momentum of those spheres and correlate those. So we know how this works. So this is something we have done already in quantum experiments with photons at first, then later with massive particles, generating, so once they are entangled, you can perform measurements on position, momentum, you correlate them, and then if the product of the conditional variances of your P and X measurements violate Heisenberg uncertainty, you know you're entangled. So this is something that is established in the literature. Yeah. Mm-hmm. Let me just emphasize, this is a long way down the road. Okay? So right now, we just want to crank the mass up, the delocalization up, and so on. So eventually having really two masses next to each other in such a configuration, yeah, who knows? It's going to take some time. You know, all the green bars need to be filled.
Can you tell us something about the discussion that the entanglement induced by gravitation is not by itself a signature of quantum gravity?
Yeah. So Adnan is referring to a recent paper that was published in Nature, saying with the title "Classical Gravity Can Entangle," something like that. Where it can generate entanglement. I cannot comment on the theory because I don't understand what is written there. I can tell you that since the paper was published 2 weeks ago, or 3 weeks ago, or 4 weeks ago, there is by now 6 different papers out there pointing out where the paper is wrong. But irrespective of that, so assuming that the paper is correct, the parameter regime that the paper is discussing effects is actually complementary to the parameter regime we are looking at. So they have a plot in the paper also where you can see that the mass regime that we are looking at is unaffected by the effects that they claim to be there. This effect will only become relevant when the masses are much, much higher. So in our case, if you look at the numbers, I did that, the effect that they claim to be out there is suppressed by 13 orders of magnitude or so. So it should not play a role. In principle, if it were there, it's interesting because then they have another knob to tune to actually test for those effects, right, if they're really there. But the current status in the literature points more towards there is much more discussion or theory side necessary.
Thanks. Okay, it's related to Adam's question. We could think of a different model, so with 1/r coupling, like electrostatic charges. Okay, you could have an electron, which is also you can manipulate, and you can delocalize an electron, and then you can ask the same question. You could have a one-over interaction and everything. So, but we have solved that already. That's quantum electrodynamics. So, do you think that if you have a positive result here, it would imply the quantization of gravity, or do you have a graviton or something like that? That's
No. So coming from quantum optics, I have learned to be more puristic with experiments. So my approach, and I think this has been the approach from the early phase of quantum optics on, is always to ask the question, what assumptions can our experiment test and hence falsify? And in that case, this is very clearly defined. The assumption is that the experiment is described through a classical field theory of gravity. This is the assumption we can test. We cannot even test whether gravity is described by Newton, because Newton is entangling, because Newton is an instantaneous interaction. Right? So in that sense, yes, the gravitational field classical gravitational field can entangle, right? But GR cannot. So this is the only thing we can say. Okay. We can, in addition, we can say, likely, if it's entanglement, then this entanglement is likely consistent with the prediction of a linearized quantum field theory of gravity, which is also fine. Yeah, so we falsify GR and we show consistency with linearized quantum field theory of gravity.
Okay. One more brief thing. So you chose very carefully your words when you started your talk about the meaning of quantum mechanics and everything. And I agree completely with what you said, but you didn't say much in the sense that, are you compromised with any particular interpretation of quantum mechanics or not? I mean, like, the realistic interpretation of the wave function, or collapse of the wave function, or many words, or anything. I mean, do you have, I think you have ideas about that, of course, but do you have a favorite interpretation for?
So I'm also always careful to stick to naming of interpretation, because the problem with naming is that people always mean something else. So, but what I personally think, except for those interpretations that have been made by a single person, so there it's clearly defined. But normally, as soon as a second person is involved, it's already diverging. So, but what I definitely can tell you is, in my opinion, is that quantum theory is a theory about probabilities of possible future measurement outcomes. And this already sets the stage then for everything that follows. And the wave function is a representation of information that we have to make those statements about probabilities.
Thank you very much. Thank you all for coming. Let's sound the speaker. Nice, Andy. Thank you very much.
Thanks. Definitely. Always a pleasure.
Very good. Thank you for coming.
Exciting. I'm amazed that the students did stay, actually. Yeah. In Vienna, they would just leave. That's great. I mean, it's really great.
You are becoming charming when you talk. You are becoming an amazing speaker. I heard you many times over the years, and you are.
Yeah, it's like. It's, how do you say, it's desperation. Because the experiments are so far away that the only thing I can do is talk now.